Welcome back to JVM Internals Crashcasts. I'm your host, Sheila, and today we're diving deeper into the JVM memory model. For those new to our show, JVM stands for Java Virtual Machine, the runtime environment for Java programs. Today we'll be exploring the fascinating world of object structure and memory layout. Joining me as always is our JVM expert, Victor. Victor, are you ready to unravel some memory mysteries?
Absolutely, Sheila. I'm excited to shed some light on how objects are actually structured in memory. This topic is crucial for understanding JVM performance and optimization.
Great. Before we dive in, let's quickly recap for our listeners. We're currently in Level 2 of our series, JVM Adept, where we're focusing on operational understanding. In our previous episode, we covered memory areas in detail. Today, we'll be building on that knowledge to explore how objects are structured within those memory areas.
That's right, Sheila. Understanding object structure and memory layout is essential for anyone looking to optimize Java applications or dig deeper into JVM internals.
Absolutely. Now let's kick things off with a quiz question for our listeners. Here's a tricky one. In a 64-bit JVM, what's the minimum amount of memory typically occupied by an empty object of a class with no fields? Is it 8 bytes, 16 bytes, or 24 bytes?
Ooh, that's a great question, Sheila. It really makes you think about the overhead associated with objects in Java. Without giving away the answer, I think this question will help our listeners understand why seemingly empty objects still consume memory.
Exactly. We'll reveal the answer a bit later. But first, let's make sure our listeners are up to speed on some key terms. Victor, could you briefly explain what we mean by object header and instance data?
Certainly. The object header is a portion of memory that the JVM uses to store metadata about an object, such as information for synchronization and garbage collection. Instance data, on the other hand, refers to the actual content of the object, the values of its fields. These two components form the basic structure of any object in memory.
Thanks for that clear explanation. Now, let's start with the basics. How is an object typically structured in memory?
Great question. At its most basic level, an object in memory consists of two main parts, the object header and the instance data. Think of it like a book. The object header is like the cover and title page, containing essential information about the book, while the instance data is like the actual content of the book.
That's a helpful analogy. Could you elaborate on what's included in the object header?
Certainly, the object header typically contains several pieces of information. First, there's the mark word, which includes data for synchronization, identity hash code, and garbage collection. Then there's a pointer to the class metadata, which tells the JVM what type of object it is. In 64-bit JVMs, this header usually occupies 12 bytes.
Interesting. So even before we store any actual data, we're already using 12 bytes just for the header. Now, what about the instance data? How is that laid out in memory?
The instance data follows the header and contains the actual values of the object's fields. The layout depends on the fields declared in the class. Primitive types like int or long are stored directly, while objects are stored as references, essentially pointers, to other memory locations.
I see. But I've heard that memory access is often optimized for certain alignments. How does that factor into object layout?
Excellent point, Sheila. The JVM indeed aligns data for optimal memory access. This often leads to padding, extra unused bytes inserted between fields or at the end of an object. For example, a 64-bit JVM typically aligns objects to 8-byte boundaries. This is why even an empty object often occupies 16 bytes, 12 for the header, padded to 16 for alignment.
So that answers our quiz question. An empty object on a 64-bit JVM typically occupies 16 bytes, not 8 or 24. That's fascinating, and it really shows how understanding these details can be crucial for memory-sensitive applications.
Exactly, and this knowledge can lead to some interesting optimization techniques. For instance, ordering fields from largest to smallest can sometimes reduce the overall object size by minimizing padding.
That's a great tip. Are there any common pitfalls or misunderstandings about object layout that developers should be aware of?
One common misunderstanding is assuming that the memory usage of an object is simply the sum of its field sizes. As we've seen, the header and padding can add significant overhead, especially for small objects. Another pitfall is neglecting the memory impact of long inheritance chains, as each superclass's fields also contribute to the object's size.
Those are important points to keep in mind. Now, how does this knowledge apply to real-world scenarios? Can you give an example of how understanding object layout might help in application design?
Absolutely. One real-world application is in designing cache-friendly data structures. By understanding object layout, you can create compact objects that fit well in CPU caches, potentially improving performance. For instance, in a high-performance Java game engine, carefully designing entity objects to minimize size can allow more entities to fit in cache, potentially improving frame rates.
That's a great example, Victor. As we wrap up, could you summarize the key points we've covered today?
Certainly. The main takeaways are: 1. Objects consist of a header and instance data. 2. The object header contains crucial metadata and typically occupies 12 bytes in a 64-bit JVM. 3. Instance data layout depends on field types and order. 4. Alignment and padding can increase an object's memory footprint. 5. Understanding object layout can lead to memory-efficient designs and better performance.
Excellent summary, Victor. Thank you for sharing your expertise with us today. In our next episode, we'll be diving into memory barriers and the happens before relationship, so stay tuned for that. And to our listeners, if you've enjoyed this deep dive into JVM internals, please subscribe to our podcast and leave us a rating. Your support helps us continue bringing you these in-depth explorations of Java and JVM concepts. Until next time, happy coding.